Okay, in this class I'm going to use differential equations to generate the master equations of kinematics. So one thing to remember is how do I define some of these things, some of these quantities from kinematics? Well, velocity we can define as the first derivative of displacement with respect to time, and acceleration we can define as the second derivative of displacement with respect to time, or the first derivative of velocity with respect to time. So these are important quantities. We're going to think about these things, and we're going to jump straight in. We're going to assume A is assuming a constant acceleration of A and an initial velocity of u. We want to find expressions for the velocity v and the displacement s after time t. So let me actually just ditch this definition here. A couple of things to note just before we get started. Really important that we're talking about, with all my master equations, we're talking about constant acceleration. The other thing that's not changing is my initial velocity. My velocity changes, but my initial velocity, which is my velocity when t is 0, so my v is equal to u when t is equal to 0. That's not changing. My velocity will be changing, but not my initial velocity. So those are constants. Constant acceleration, constant initial velocity. A and u are constant. So with that in mind, I'm going to look at something. So acceleration, we know, is the second derivative of position with respect to time. We also know that velocity is the first derivative of position with respect to time. So the derivative of velocity with respect to time is the second derivative of displacement with respect to time. Okay, it's a bit like our v substitution we were using earlier on. V equals ds dt, so taking the derivative with respect to t, dv dt equals d2s dt squared. What I'm going to do is I'm going to take this value dv dt and I'm going to substitute it in for d2s dt squared in here. So therefore, dv dt is equal to a. dv dt is equal to a. What am I going to do? Well, it's a differential equation because it contains a derivative. I'm going to separate dv dt equals a. That means dv equals a times dt. Remember, a is not variable here. It's a constant, so we just treat it like a constant. And now I'm going to take the antiderivative on both sides. The process of taking that antiderivative is called integration. I'm going to integrate on both sides. Really straightforward. On the left hand side, the antiderivative of 1 with respect to v is just v. On the right hand side, the antiderivative, a times the antiderivative of 1 will be at, and then we have our constant of integration here. Okay, so that's my general solution. V is equal to at plus c. To find my initial solution, I look at, or my particular solution, I look at my initial conditions. So, but v is equal to u when t is equal to 0. Why? Well, because we were told the initial velocity is u. That's what initial velocity means. When the time is 0, what's the velocity? Therefore, substituting u in for v and 0 in for t into this equation, u in for v, 0 in for t, we get u is equal to c. Which means, of course, that the velocity, my particular solution, is v equals at plus u, or the more familiar way we would see that is v is equal to u plus at. And that's my first master equation. We've spoken about that before. V is equal to u plus at. So that's useful. If we know the acceleration is constant, of course, and if we know the initial velocity, well then the final velocity is going to be the initial velocity plus the acceleration by however much time has passed. But it depends entirely on acceleration being positive. Okay. So that's my first master equation. Remember also that V is equal to ds dt. V is ds dt. So we're going to use that substitution now to solve this equation one more time. So V is equal to ds dt. I'm going to do that over the page. So what have we found? Well, we've just found that V is equal to u plus at. We know from our substitution that V is ds dt. So I'm going to use that substitution in here. ds dt is equal to u plus at. Differential equation, first order, it's separable, so I'm going to separate and integrate. I separate by multiplying on both sides by dt. And now I integrate, take the antiderivative on each side. On the left hand side, the antiderivative of 1 with respect to s is s. Over here, the antiderivative of u. Remember, u is a constant. That's important to remember. U is a constant. So the antiderivative of u with respect to t will be that constant u times t. Plus, I'm going to factor out the a and take the antiderivative of t, which will be t squared over 2. And then plus the constant of integration. So, oops. Well, what do we know? Well, what do we know? I'm just going to examine my initial conditions. But s equals something when t equals 0. Well, when t equals 0, what is displacement? Displacement is change in position. So when no time has passed, there can be no change in position. So s equals 0 when t equals 0. So I'm going to substitute those values in. Therefore, substituting 0 for s, 0 equals ut is 0 because t is 0. At squared over 2 is 0 because t is 0. 0 is going to equal to c. So therefore, we can write s equals ut plus at squared over 2. We're more used to seeing that written as s equals ut plus dividing by 2 is the same as multiplying by a half at squared. So this is useful stuff. What are we saying? If we know the acceleration is constant and we know our initial velocity u, well then the displacement after t seconds will be ut plus a half at squared. So there's two important master equations generated. Okay, we're going to look at generating one more, and I'll look at that in the next class.